Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 12 Physical Sciences Work Energy and Power series. In today's video, we showing you how to pass this topic. So basically, this is a summary of this topic, and these are the tips you will need to pass your examinations. So this particular question, when you get to it, it's important you know all definitions. Okay? It's important to note all definitions. The key definitions in this topic, which we have seen quite a lot, is that you need to know your work energy theorem. You need to be able to state it in words. Okay? You need to be able to state the law of conservation of mechanical energy. Okay. The law of conservation. The law of conservation of mechanical energy. You need to also know the definition of power. Okay. You also need to know the definition of power. Let's zoom this nicely. Okay. You need to know the definition of power. Then you need to know the definition of conservative force. Okay, the definition of conservative force and that of a non-conservative force. Okay, and that of a non-conservative force. Okay, these are not the only definitions there is to know in this particular topic. There's a lot of them, but knowing these, you are good to go. Okay, knowing these, you are good to go. Now, the second part will be the calculations. What do you need to know for your calculations? Remember, it's important that before you do anything in this particular topic, it's important that one, you draw your free body diagram. Okay, it's important that you know, or rather, you draw your free body diagram. So this shows all the forces acting on the object, whether they are doing work or not, but you need to know this. I'm going to give you an example of, maybe I should try two, an example of an object being pulled horizontally, and let's say it's a rough surface. So such an object, if you draw a free body diagram, you will say one, you have normal force, which is equal to the gravitational force. Okay, which is equal to the gravitational force. Then you have applied force and friction, right? This is the free body diagram for such motion. Now let's consider when your object is moving on an incline. Now let's say an object is moving on an incline, or rather it's pulled on an incline by force F. Okay, so with this, you will need to, and I'm going to call this the ramp, let's say it has a slope alpha. Okay, so with this, your free body diagram, you have two ways of drawing it. One, draw the force of gravity which is perpendicular to the ground. I'm not saying perpendicular to the surface, I'm saying perpendicular to the ground, and the normal force which is perpendicular to the surface that the object is moving on. Then you have your applied force here. We said this is a rough surface, so the object will also experience some friction. Okay, if you do not like it in this way, you can resolve your gravitational force and have it in this way. Let's say this is your normal, and then this is your vertical component of gravity, which is F sub gy, and then this will be your horizontal component of gravity, F sub gx. Of course, friction in this way, and then applied force in that way. Okay, applied force in that way. Okay, so this is the free body diagram that you're going to come across. Now for this one here, when you resolve gravitational force, you will say sine, I said the angle is alpha, sine alpha is F sub g x over F sub g, right? And you can also say cos alpha, not theta, we said alpha. So cos alpha is equal to F sub gy over F sub g. So further, we can say F sub gx equals F sub g sine alpha, whereas with this one, we can say F sub gy. So F sub gy equals F sub g cos alpha, right? Perfect. So what do we know about F sub g? We know that it is mass times gravitational acceleration. Okay, it is mass times gravitational acceleration. If you can know this, you are good to go. Okay, if you can know this, you are good to go. Okay, so this is how you resolve. This is how you resolve your gravity. Okay, this is how you resolve your gravity. Okay, this is how you resolve your gravity. These are the components of gravity, the horizontal and vertical components of gravity. Okay, now let's go to this first part was using three body diagram. Now let's go to the part where the second part will be energy. And here we need to recall that when we talk of energy, we're talking kinetic energy. We know the formula is half times mass of the object and speed of the object. We also have potential energy. The formulas are given, guys, in your information sheet at the back of your question paper. They are given. Potential energy, it is mass times gravitational acceleration times height of the object. And then we have what we call mechanical energy. What is it? Whether you say EM or M or E mech, it doesn't matter. It is E sub K plus E sub P. So mechanical energy is the object sum of kinetic energy and potential energy. Okay, perfect. Now, this, you can calculate kinetic energy at any point in your motion. Same applies to potential energy, even mechanical energy. You can calculate them at any point. Now, in this one, this will also lead you to the law of conservation of mechanical energy. Right? The law of conservation of mechanical energy. It's important that you know it. Law of conservation of mechanical energy. Remember, we said mechanical energy of an object is the object sum of kinetic and potential energies. Right? So that means mechanical energy at one point is equal to mechanical energy at another point. Remember, this is only if the only force influencing the object or the motion is gravity. Okay, but if there's any other force except gravity, mechanical energy will not be conserved. Okay, so for this to apply, only applicable if gravity is the only force. Okay, is the only force acting. Okay, is the only force acting. Okay, if you have any other force, to be precise, if you have non-conservative forces, this law will not apply. Okay, if you have non-conservative forces, this law will not apply. You have seen it occurring a lot when they say, suppose this, let's say it's AB. They say, suppose it's smooth and your object is sliding down the ramp. if there is no other force affecting this object. This is where you will say, oh, kinetic energy at point A plus potential energy at point A will be equal to kinetic energy at point B plus potential energy at point B. You get it? And this is how you have been using it. Okay? And this is how you have been using it. And this is also how you can use it. Only if there is no other force affecting this object or the motion of this object in this path. Okay? Perfect. Now, let's then we're now going to look at, I believe this is the third aspect. We're going to look at the work done. Okay? Now we're going to look at the work done. For the work done, it's important, guys, to know that the formulas are given. Okay? It's important to know that the formulas are given. There is one which you call, before you proceed, work done is equal to the product of the force applied times the displacement in which the force is applied in, multiplied by the angle between the force and the displacement, isn't it? Perfect. So now you need to know this. You have the work energy theorem, right? You have the work energy theorem. I told you you need to be able to state it in words. The work energy theorem, we know that it says net work is equal to change in kinetic energy, right? So for that object that we were looking at when our object was sliding up the incline, or maybe we can also use the one where it is being pulled. Okay, where it is being pulled. Okay, we can also use one where it is being pulled. Where is it? Yeah. Yeah. Okay, here is it. Where we use one where it is being pulled, you will say, let me show you how you use your work energy theorem. So with this one, you will say, let's say our object is being pulled this way and there's some friction there. So your network here will be the work done by the applied force plus the work done by friction. Why only these two? Because they are the only forces that are in the direction of the displacement. Right? Perfect. So therefore, this means work done by the applied force plus work done by friction will be equal to change in kinetic energy. Isn't it? Now, what about on an incline? Remember, I drew the free body diagram for this one here. All right. So what about on an incline? If you use the work energy theorem here, the net work will be, if you recall the free body diagram, the work done by the applied force plus work done by friction plus work done by horizontal component of gravity, F sub gx. Right? So these terms are your networks. So you will then say, okay, work done by applied force plus work done by friction plus work done by F sub gx equals change in kinetic energy. Right. Okay. Alternatively, you can also find F net. You can say F net equals applied force plus force of gravity. Okay? And with this one here, you can say F net equals applied force. Sorry, this is not force of gravity. This is a frictional force. All right. Let me fix that mistake. But I did write frictional force. But with this one here, it's applied force. It's applied force, frictional force plus horizontal component of gravity. Right? Plus horizontal component of gravity. Right? So these, you then place them into, you can say now net work equals F net delta X. Right? So having said that, you can then say, oh, you know your net force. Now knowing your net force, you can substitute it here into this equation, multiply it with the displacement, you get your net work. Okay, that is another way. Okay, that is another way. So, and Now, I also need to talk about this part here. We need to talk about this part we call the frictional force. Shall we? Let's talk about the frictional force. But before that, let's talk about work done by a non-conservative force. Okay? Let's talk about work done by a non-conservative force. Okay? So we will now talk about work done by a non-conservative force, or work done by non-conservative forces. Let me not say A. Work done by non-conservative forces. Okay, so work done by non-conservative forces, the formula is also given. It is W sub NC equals change in kinetic energy plus change in potential energy. So with this, what are you doing? You're looking at your non-conservative forces. For our cases that we were looking at, you recall this one here and this one here. You guys remember them, right? Remember, with this one, the non-conservative forces here are friction and applied force, right? The non-conservative forces here are friction and applied forces. So here, you do not need to waste your time. It will be this work done by non-conservative force. Applies for both of them here, okay? Will be work done by applied force plus work done by the frictional force. You do not include work done by horizontal component of gravity. It is not a non-conservative force. Okay, you do not include it. So in other words, this therefore says to us, work done by applied force plus work done by friction equals changing kinetic energy plus changing potential energy. Remember, this formula can work at all times. You just need to know whether you have a non-conservative force or you don't. If you don't have a non-conservative force, this formula will become law of conservation of mechanical energy, because work done by non-conservative force will be zero. So this work done by non-conservative force is basically saying to you the network of all the non-conservative forces acting on the object. Okay, so if you have them, guys, you are good to go. All right, perfect. Now, the next one that I want to look at, I wanted to introduce it before I almost forgot that I need to look at this part. Now, let's look at this part here, which is frictional force. Okay, I want us to look at frictional force. It's important that we look at frictional force. Guys, the value of the frictional force can be given to you, but in cases where it's not given to you, you know that when the object is moving, kinetic frictional force will be equal to coefficient of kinetic frictional force times the normal force. Okay. The scenarios that we were looking at so far, or that we are looking at so far, will say to you normal force is equal to applied. So I want to introduce it in this way. We're now gonna extend it and say, let's now imagine our object being pulled by this force here, and of course it experiences a frictional force. And then let's also imagine one being pulled at an angle. Okay, let's imagine one being pulled at an angle. So now let's do a free body diagram for this. Like we said, it will be normal and force of gravity, and then friction applied and friction. Right. Now with this one here, it will be a normal and force of gravity. Then you will have applied force here at an angle. What angle? Angle alpha. And you will have force F, which is the frictional force, right? Now, here, what is our friction? I'm going to show you. So we said friction is mu sub k, which is coefficient of kinetic friction, times the normal. Here, we can simply say the normal is equal to F sub g, which is mass times gravitational acceleration, right? But what about here? We need to be careful. N plus, you need to resolve this applied force into horizontal and vertical component. So all the forces in the vertical will be normal plus F sub y, they going in the same direction, and F sub g is going in the opposite direction. So resolving F sub y, we will have F sine alpha. And we said F sub g is mass times gravitational acceleration, right? Perfect. Now this therefore says our normal force in this case is mg minus F sine alpha. Remember, this alpha is the angle that is pulling the object, right? So this is the angle between the horizontal and the applied force. Okay, so it's important that you note this. Now you can now see that, okay, here kinetic friction is equal to mu sub k, coefficient of kinetic friction, times mass times gravitational acceleration. Sort of straightforward. But in this case, it is not. Kinetic friction is mu sub k, open bracket, mass times gravitational acceleration minus applied force times sine alpha. You get it? This is what you need to know. If you can know this, trust me, guys, whatever question comes your way, you will be able to crack it. Okay? All right, perfect. Now we're going to conclude this with the last one being power. Okay, the last one being power. So power, it's also one term that you need to know its definition. It has the formula power equals work over delta T, or power, which is average, is equal to force times average velocity. So these ones, how do we use them? Let me see the writing here. Okay, it will be awful. Let me just change the color. This green would do. So this, you will use as is if it's a constant speed. Okay, constant speed. Or you will say it is total distance. If you're not given a constant speed, you will say this constant distance over total time. So not constant distance, total distance over total time. This is how you can find your average speed. Okay, so this average speed you use as is if you are given your constant speed, or otherwise if you are given the distance and the time it takes to cover the distance, this is you finding your average speed. Okay, so this power equals work done per unit time. So if they say power of walking, you will need the work done, or the work done to move. All right, in other words, you will need the force that you need to move. Examples will be, what is the power of the engine? You will need to know the force of that engine. All right, so if you know the force of that engine and the displacement or the distance that vehicle has moved, you can easily find your power. Okay, these guys is all that, or rather, these are all that you need to pass your work, energy, and power exam questions. Okay, it's important that you know these things. Now, I want to add a point here. Remember, we said, okay, let me go back to my normal color. Remember, we said, so note, remember, we said work equals F delta X cos theta. Okay, it's important to note, for example, I'm going to show you now. It's important to note for this block, I had said if you draw its free body diagram, it will be something like this. Okay, it will be something like this. Okay, it'll be something like this. All right. So you need to be careful with when we were using work energy theorem. I had said when you use work energy theorem, I had said this will basically be work done by applied force plus work done by friction equals changing kinetic energy. It is not a mistake that I said plus. Okay. Why did I say that? It's because one, you will say work done by applied force will be force times displacement cos theta. That force being whatever value it is, displacement being whatever it is. Now, where is this applied force going? It is going in the direction of the displacement. If it is going in the direction of the displacement, the angle is 0 degrees. Now, cos 0 is positive. So this means applied force does positive work. Okay? Now, you look at that of friction. All right, you look at that of friction. All right, you look at that of friction. The force is small caps F delta X. What is the angle? This, as you can see, it is in the opposite direction, so it makes 180 degrees. We say it's 180 degrees. This therefore becomes minus F delta X. So friction does negative work. Now, if you were to look at it, you will be saying, now, you said W net equals change in kinetic energy. What is this? It's F delta X minus F small caps F delta X equals change in kinetic energy. So this was not a mistake. Okay, this was not a mistake. What I need you is for you to be careful with the signs. Okay, be careful with the signs. Guys, this is all that you need to pass this topic. Okay, this is all you need to pass this topic. I hope you guys are good and see you next time and all the best. Bye bye.